And you will see that there are a lot of scope in research and finding out new algorithms, working on new techniques that will revolutionize a lot of things that you do each and every day. So just give me a moment. So, uh, in the 1950s, when artificial intelligence was slowly being introduced into the field of computer science, people started with creating computer programs that can actually, play with a human being and maybe try to defeat him. So in 1950s, there were a lot of programs that were developed in this kind of a exercise, and in 1960s, there were programs that came up which started defeating human beings at games like chess or Jeopardy, which is a game which IBM had used to introduce their Watson AI machine that they developed in the 70s to defeat humans at these kind of games. And what these games are about is that they are mostly centered about decision making. So whenever you want to play your move in a game, whether it be chess or poker or checkers or AlphaGo, you have to decide on a particular move. So you will think that, okay, this is a move that I want to make in order to defeat the other player. So when you think about a move and when you try to understand as to what should be your move, what you do basically is that you try to emulate the other person's thinking in that move. So you think that if I play this move, what will the other person move, and how can I even think in terms of, let's say, 5 or 6 moves ahead of the other player. So computer scientists thought about this thing, that if they can emulate a person using a computer program. For example, if there's a computer program that can actually think about 5 or 6 or 10 or 20 moves in advance, then the human player will not be able to catch up. So the reason is that a human mind has a certain limitation. So you can maybe think of 10 or maybe 5 or 6 moves in advance, but thinking about 50 or 100 moves in advance is extremely difficult for a human being to do. So this is how these initial games were developed, and slowly in the 1970s, we saw that a lot of computer programs were developed mostly by IBM, who actually started this kind of a venture to defeat seasoned human players and chess grandmasters. So recently, you might have seen the news around 2012 or 2013. There was a program by Google that defeated the most advanced human player in AlphaGo. So that was a remarkable achievement, and the background of that particular computer program was a deep learning algorithm that was running, and the human players were not just being able to catch up with that algorithm. So what it shows basically is that if we can emulate or if we can mimic a human being through a computer program, then that is what we call as artificial intelligence. And a very advanced version of artificial intelligence is deep learning, which is derived from machine learning theory, and machine learning again is a part of artificial intelligence. So I'm still waiting for my slides. So what we did in the 1980s and 1990s is that we tried to go deeper into the human brain, or in the human sense of understanding as to how do we do our daily tasks. For example, let's say making a decision, thinking about some problem, reasoning, emotion, learning to speak, learning to write, learning to understand images, videos, and so on. So the human brain, as you know, consists of several neurons. So these neurons are basically interconnected with each other, and there is an electrical signal that flows through these neurons, which basically drives all our decision making capabilities. So if we can simulate a human brain in a very primitive manner, because we don't have a complete understanding of the human brain, then what we can do is we can actually mimic as to how the human nervous system operates. So then came neurons, or artificial neurons as they called it, in the 1980s. So in 1987, a scientist called Jeffrey Hinton and his lab mates, they came up with an algorithm that they call backpropagation, which actually allowed to train an artificial neural network to do tasks that a human can do. Okay, so artificial neural networks are not exactly as the human neural network operates, but they are kind of an inspired version of the human neural networks. So when these artificial neural networks came into being, there wasn't enough data, to even test these kind of models or test these kind of computer programs as to what the capabilities are. So nowadays you'll see that there is no dearth of data. So there is a huge amounts of data. So every day on YouTube, there would be millions and thousands and millions of videos that are being uploaded. There are lots and lots of images on the internet. There is huge amount of text data. So there is no dearth of data. And due to this age where so much of data is being created, it gives us, a chance to test these kind of neural networks. And what we did then was that try to train these neural networks on tasks that human beings would be able to do. For example, classification, clustering, understanding, making decisions, recognizing people from images, and so on. So yeah, thank you for that, Sandeepan. So now, so machine learning basically is a process by which a system can make decisions or predict outcomes of events based on input data.
Dr. Ghosh, I am just interrupting you. Is it visible, the presentation?
Yeah, it's visible. Yeah. Thank you.
Okay. Is it the right slide you are talking?
Yeah, I can start from this. Yeah.
Okay, thank you.
So, yeah, and I'll tell you when to just move on to the next slide until my system comes up, which it will come up in maybe 5 minutes. So, so machine learning is this exciting new field where you can allow machines to learn from data, and this is something that all of human beings will do. So we learn from our daily experiences. We learn from whatever we see in your daily life. When we are a child, we understand what is the difference between right and wrong. What is the difference between walking properly or falling down. So there are different feedback paths that are there in the nervous system. For example, let's say when we learn to walk, what we try to do is that we try to walk in a particular way in which we will not fall down. So when we fall down, we get hurt, and that hurt thing is basically a negative signal that goes into our system and says that if you walk this way, you'll fall down and you'll get hurt. So next time you have to try better. So this is basically what machine learning is, and it's basically the science of building programs that can actually learn from experience. Next slide, please. So let's try to understand a simple machine learning method. So very simply, if I put it, so for example, you see a graph on the right hand side. So let's say I want to understand, a bank, let's say, wants to understand whether he should give loans to a particular customer or not. So if a customer is a high risk customer, for example, let's say if he is not likely to return the money of the bank, then the bank shouldn't give loan to that person, right? But if a person is a low risk customer, then the bank can give him loan. So what differentiates basically a high risk customer and low risk customer? So the bank will look at very simple things, for example, your annual income, your savings, and so on. So if I just take into consideration two things, for example, savings and annual income on the right hand side in the graph that you see, then I can understand and see that people, those who have high income and high savings, are basically low risk customers, and people who have low income and low savings are high risk customers, because they will not be probably able to return the loan when they take that from the bank. So when this happens, what will happen is that if we develop a simple rule, for example, let's say if income greater than theta1, so theta1 is a threshold, okay? For example, let's say if income is greater than 10 lakhs per annum and savings is, let's say, greater than 4 lakhs or 5 lakhs per annum, then that person can be given a loan, right? So this is a very simple rule-based methods which banks have been doing for the last 150 years. But this basic thing can actually be converted into a machine learning problem. Next slide. So this is the old rule-based method. For example, if you want to understand whether you should accept a job or not, right? So in that case, what you'll be doing is you will be making the decision based on certain parameters, right? And these parameters are, for example, do you have free coffee offered at the job? Do you have your salary at least above a threshold? So do you have to commute for a very long time? And then based on these several factors, you can actually make a decision. So this basic thing is known as a decision tree, which was one of the first machine learning methods developed in the 1960s, right? So what a decision tree does is it looks at several parameters, and then it basically, you know, comes up with a decision. So you move from the top to the bottom in the decision tree, okay? And whenever you hit a leaf node which says either an accept offer or decline offer, you make the decision, right? So next slide. So now, can we do it as a computational process? So let's try to bring the power of computers now, because we are trying to move from a rule-based system to a completely automated system. So a completely automated system will basically, try to again plot this particular data that we have now. For example, let's say we already have some data about people. So this is about whether a student is good in science or not. So there's physics and mathematics, maybe two subjects that you can choose. You can choose others also. We have chosen two subjects. So now you see that this data is basically, driving a lot of decisions that we can make. So there are two things here I'll be introducing. So first thing is the training set and the testing set. So training set basically is the data that we have beforehand, okay? And testing set is basically the data that we can probably, test the network or test the algorithm on and see whether the algorithm is doing the right thing or not. So you see those stars in this diagram. So these stars are basically the testing data. Now, this is a very simple algorithm called nearest neighbor. So what you do basically is when you plot this, let's say when you plot these different points on a two-dimensional scale, and you see this particular thing that is being developed. So you see on the right-hand side of the training set, you have a lot of people with that, round, the blue circles and the green circles. So in order to make a decision when you have a testing data, what you do basically is that you see which is the nearest point in this two-dimensional scale for the testing data, okay? So if that nearest point is, let's say, somebody who should be considered a student good in science, you take that. If it's not, you take the other one. So this is a very simple way of doing classification, and we'll see how this thing is again, advanced in the recent era. Next slide. So this is the entire jargon of machine learning. So machine learning has a lot of different fields, like like supervised learning, unsupervised learning, and then there is classification, dimensionality reduction, clustering, reinforcement learning, and so on. I'll be talking about some of them, not all of them, because we have limited time. So you see on the leaf nodes of this particular diagram, you have several applications. So you can see for classification, you have image classification, identity fraud detection, diagnostics. You have in regression, you have weather forecasting, market forecasting, population growth prediction. Reinforcement learning, you have games, you have learning tasks, robot navigations, real-time systems. And in dimension reduction, you have big data visualization, structure recovery, and so on. There are a huge number of applications where this is relevant. And this is really exciting because now machine learning has entered into every single thing that we wanted to do using computers, right? So this particular thing is really, really interesting, and people have explored a lot of different variations of these machine learning algorithms. So I'll be speaking about some of them. So let's just dive into some of these things. Next slide. So what is supervised machine learning? So supervised machine learning is nothing but, giving the algorithm some kind of supervision. Okay. So what do we mean by supervision here? So supervision basically here means that if you tell an algorithm, let's say if you want to return back to home from work, okay, so based on your past experience you will make some predictions, okay, and we want these algorithms to make predictions. That's what we want. And if we can make predictions, we can do every single thing that we want to do. So let's say there are different parameters on which you will think. For example, let's say weather conditions, time of day, holidays, route chosen. So different parameters based on which you can decide that at what particular time you will be reaching home, right? So if you reach home really early, that would mean maybe the weather was good, or maybe it was a holiday, or maybe you chose a very nice route where you did not get any traffic jams and so on. So these parameters are known as features. So we call these things features. And based on these features, we try to build a computer program which can actually train itself, right? So I think Shondipan, my slides are probably up. Maybe I can join from my uh, account. Just give me 1 minute, okay? I'm just rejoining.
Okay, I'm stop sharing. Dr. Ghosh will start his slide.
Yeah, am I audible?
Yes.
Yeah. So
Yes,
yeah,
sir.
yeah. So let me just. I think there's some problem. Maybe Shondipan, you can reshare your screen. So it might take some time. So let me continue here. So I was talking about supervised learning. So supervised learning is basically, trying to build a system where we already have a lot of past experiences, and using these past experiences we can make predictions for the future. It's as simple as that. And we do these things in our daily life, right? Daily we would like to understand what will happen at each time of the day, or what will happen to me if I do this and if I do that, based on past experiences, right? So this is what is supervised learning is. So next slide. So then there comes unsupervised learning. So what is unsupervised learning? So unsupervised learning again does some learning based on data, but now we do not have these labels. So by labels, I mean that we do not have the outcomes of these predictions that we want to make. For example, let's say, you know, uh, I don't teach you what is good and what is bad. So I just tell you that, see, these things are there, you can make these decisions or you can make that decision, right? But I don't tell you this decision is good or that decision is bad. So then how do you learn from that data? So what you do basically is you group the data into different types. So you can see these are images of some vegetables and they are of different color or different shape. So what you can do is you can cluster these things into, the same kind at one place, and that would give you a kind of grouping that you want to do. Okay, so by grouping I mean that you can basically keep the similar things in one place and differentiate with the dissimilar things. So this is unsupervised learning. We do a lot of unsupervised learning daily. For example, um, Jan LeCun, who is considered as one of the fathers of deep learning, had once said that most of the learning that takes place in human beings are unsupervised learning. So unsupervised learning then became a really exciting part of machine learning, and this again brings us more and more closer to what human beings will do in their daily lives. Next slide. So let's try to understand this particular term, which is classification, which we'll be using in our presentation. So classification is the very, very fundamental thing that we have in machine learning. So classification is nothing but assigning a class to a particular data. Okay, so data can be anything. It can be an image, it can be a video, it can be some text, it can be some experience, it can be something, right? Anything which will, consider some kind of input signals that we take, right? So let's say I want to classify an image into either, let's say, a cat or a dog or a truck or a plane or some kind of object, right? So let's say these objects are predefined and I want to assign this particular label to this object. So this assignment of label will be done by a model, right? Which, let's say, you humans can do that very easily. We can see an image and we can say that there's a cat and a dog. But we want to teach a system whether it can do this kind of a classification task. Okay, next slide. So I think Sondipan, these slides are the older ones. I'll just mail you my new one. So just give me a minute. So while I do that, so this is an example of a classifier, that we use every day. Okay, so these classifiers are nothing but, for example, let's say a mail spam classifier. For example, you have an email that you have with Google. Okay, so that email, what does that do? That has different sections, right? Inbox, you have outbox, you have sent, and you have spam, right? So spam are those emails which are not relevant to you. Okay, so those are really, I would say, ones that you don't want to see, right? You don't want to see any spam. So when you don't want to see any spam, what Google does for you is that Google basically filters out all of those spams for you, and then it basically maintains a spam folder, right, where it puts all of those spam mails. So how does Google understand whether what is spam and what is not, right? So in order to understand this thing, what Google does is it looks into, the mail that is being sent, right? So when it looks into the mail that is being sent by you by somebody, for example, would say, you have won a reward, or you have won a very big bank loan, you have won a cash award, you can collect your award from these places and this. So whenever we see those mails, right, what we do is that we generally ignore those mails. Why? Because we think and we understand that those mails are probably not real, right? So when we discard those mails, we are basically doing a classification task. Now Google, in this case, will do that classification task for you, right? So when Google does that classification task for you, that's a very simple classifier that Google builds. Okay, I'll just mail my recent slides on the one. I think this is the old one. So you can directly go to the neural network slide, maybe 4 slides from this place. Yeah. So let's start with a very simple model and a very advanced as well, which we are using each and every day with our different algorithms that we build in deep learning, right? So neural networks are probably the most advanced version of machine learning algorithms, but they are very fundamental as to how we can bring humans and machines closer to each other. Okay, so next slide. So what is a neural network? Let's try to understand the thing first, and then we can go on to some advanced things. So a neural network basically is nothing but a set of nodes, and these nodes are basically emulating your neurons, right? So these nodes are nothing but the neurons that we have in our brain. So they are just a simulation of what we have inside. So you see there's an input to this network and there's an output to this network. So in the input, you give, let's say, an image, okay? And I'll talk about how you can give an image as input. So when you give this image as input, what you have basically is you have some hidden layers, right? And you have an output. So these connections that you see in the hidden layers, right? These connections that you see, these connections are nothing but, some weights which basically connect two nodes. So a weight is nothing but a number, for example, let's say. So let's say if I convert the input, which is an image in this case, into a set of numbers. Okay, we'll talk about how we do that. But if let's say if we can convert that, we can multiply these numbers by some weights at every layer and then get an output in the output layer. Okay, so that output layer, which says either it's a cat or a dog, will also be determined by a number. So we know that computers only work on numbers, and using numbers only, we can actually emulate as to how we can build a classifier using this artificial version of a neural network. Okay, Sandeepan, I think I have mailed my slides. Maybe you can take the latest one and then reshare. Till then, I'll just continue from this. Okay, so now if we, let's say if we build something like this, how do we teach this network? How do we train this kind of a network? Or how do we make a network which on given an image will do this job absolutely perfectly every time? Okay, and that is what we want. Next slide. So while he puts up my slide, so can any one of you guess whether there is any problem? Or so I would like to make this interactive. If you have a question, please feel free to interrupt me and ask. So this particular model, it's a birthplace of where deep learning and machine learning started, and this happened in the 1980s, late 1980s. But in the 1990s, people were trying to train these networks. They're trying very hard, but the computational capability of computers at that particular time were not very high. And you can guess from this particular network, there would be so many weights that are there, right? I have given a very simple version of a neural network. A real one would have maybe thousands and millions of such neurons. Okay, and you can guess the number of weights. So for example, they'll go up to billions. So the most advanced neural network that we have now will have several billions of such weights, doing very, very advanced tasks, for example, with predicting weather and understanding people's emotions and so on, right? But this started from this very cat and dog example. And this experiment was conducted by Google in 2009, I think, if I remember correctly. And they, used a cluster of machines, lot of machines at that particular time to train this kind of a network only to do a cat versus dog classification. So you can imagine as to how primitive this area was even in 2008 or 9. And we were trying to do cat versus dogs, where our goal is, to emulate humans or to, exactly be like how humans are. So, Sandeepan, if you have got my recent slides, maybe you can share that. So while he does that, maybe you can just a second. Yeah, so while he does that, so we like to understand how a neural network works, right? And in order to understand that, what we'll have to see is that these weights, Sandeepan, maybe next slide you can just go on to the. Please pardon me for all of this interruption. I'm really sorry. Okay, so this is how a neural network looks like. Okay, so this is a kind of a mathematical version, not a very detailed version, but to some extent it has more detail than the previous one. So you can see this x1, x2, x3, xn. These are all the inputs, right? So these inputs will come from your input image or input, whatever input you have, which you want to classify. Okay, so when you pass these inputs, they are passed through these layers, and while they pass through these layers, what you do is that you multiply every input signal with these weights, take a summation of them, and then pass on to the next layer. Okay, as simple as that. So now the question would be, okay, so if you are trying to do something, is it very similar to what humans do? Okay, so we don't know exactly how the human neurons work. We have some level of understanding, but this is not exactly how it works. Okay, but all we are trying to do is emulate, trying to simulate and trying to see whether doing something of this sort can achieve our goal. Okay, so you'll see that these hidden layers, so there are two hidden layers. So hidden layers are nothing but the intermediate layers between the output and input, and you can have as many hidden layers as you want. So there are 2 layers here. You can have 10 layers, you can have 15 layers, you can have hundreds as well. Okay, so to my mind, when I think about this, a very simple explanation is that if you have more of hidden layers, you'll have more of weights, and when you have more of weights, you will have a better control over this transformation process. So what is this transformation process taking place here? So you are changing the input to the output. Okay. So in the output, you want a decision. You want that classification decision, whether it's a cat or a dog. So you'll see there are several output nodes also. There is y1, y2 to yn. So, okay. So this is a very general diagram. So the output does not have to be limited to only one node. It can be maybe 10, 15, 20 nodes. And that will depend on what kind of decision you want to make. Okay. So now what you do is that you have to update these weights in some way so that the neural network becomes more and more perfect or more and more correct at making these predictions. Okay. Now the question is, how do you update these weights? So you don't know, right, as to what kind of weight it will have, right? So when you update these weights, you use an algorithm called backpropagation. So this backpropagation algorithm was invented way back in 1986 by Jeffrey Hinton's team. But people were using it, but this algorithm was not very efficient. Okay, it was not very efficient at doing backpropagation when you had too many hidden layers. So if you have 1 or 2 or 5 hidden layers, it works very good. But if you, let's say, want to have 500 hidden layers, let's say, okay, then it will not work very well. The reason is the weights do not get updated very nicely at that particular way if you have a lot of hidden layers, because there's a syndrome known as vanishing gradient, which is a mathematical idea. I'll not go into it, but then you cannot have too many hidden layers. Okay, that's a restriction that was there until 2006.
The sound problem, it is not audible. Dr. Ghosh, you are not audible.
Yes, it's not audible actually.
No sound is coming.
It's not audible still.
Sir got disconnected, I think.
Wait just a minute. He has
Just a minute,
disconnected.
just a minute.
Please wait. He has disconnected.
Am I audible?
Yes, you are audible.
Yeah, I'm sorry. I think something happened with my microphone. So what I was trying to say is that what we are trying to do here is we are trying to train this neural network in making a more and more accurate decision, right? And the way in which the way in which we are doing it is basically what we do is we construct something known as a loss function. So that loss is basically a metric or a quantity which says that how much error we are making. Okay, if you go to the previous slide, yeah, I just speak for 1 minute on this because I think you didn't hear me. So I gave a technical explanation. So I'll just repeat that. So you construct a loss function with the outputs, right? And what is that loss function? That loss function can easily be, let's say, if I give 100 inputs, how many errors I'm making out of 100, or how many things I'm making correct. So the more and more errors I make, the higher is the loss. The less and less errors I make, the lesser is the loss. Okay. For example, just let's assume that for a moment. Now, how can we update the weights in such a way so that this loss is decreased? Okay. So one way to do that is take the derivative of that loss with respect to the weights. Okay, so when I say with respect to the weights, if there are, let's say, 100 million weights, so there would be 100 million derivatives with the loss. Okay, and these derivatives are nothing but something known as gradient. So a gradient is basically, what it says is, if you change the weights by a very small quantity, how does the loss change? Okay, because what you want to do is you want to change the weights in such a way so that your loss is minimized, and loss minimized means your network is making better and better predictions. Okay, so if you continue doing this in an iterative fashion, okay, every time you give some inputs, you get some outputs, you construct that loss, you find out what the loss is, which is again some mathematical quantity I've not just mentioned here for simplicity. You construct that loss and you take the derivative of every weight with that loss that you get, and you update the weights with the negative of the derivative. Why negative of the derivative? Because you want to go in a direction opposite to increasing loss, because you want to decrease the loss, right? So you put a negative in front of the gradient and you update the weights with that loss. If you do that and you keep on doing that, what will happen is the weights will change in such a way so that your loss is decreased. And when your loss is decreased, your prediction will be more and more perfect. Okay. So what happened due to this is in 1986, when this was introduced, people started using this thing to do some very simple tasks. For example, let's say classify, not images were not used at that particular time. People used to do on sentences or text or something of that sort, and they used to do very simple classification stuff. For example, some examples that I gave you, right? What is the what kind of what at what time I would reach home today, or should I take this job offer or not? And in the input, they used to give those features. For example, for a job offer, they'll give features like salary, what is my perks, what are my benefits, other benefits, how is the work atmosphere, and so on, using some numbers. Okay, and they try to mimic a human being who can make these decisions in a better way. Okay, so once you do that, you have a neural network that can take some inputs and produce exact kind of predictions which a human will make, because you have trained this neural network using data which are labeled by humans, and from that experience this networks updates its weights in such a way so that next time when you give an input, you can expect a very good or near perfect prediction. It will not be absolutely 100% perfect, but it will be a near perfect prediction. So if you give, let's say, 100 inputs, you can expect something of that, let's say 90 or 95 predictions would be correct, right? So once you do that, so isn't this a very simple emulation of a human brain? A very simple emulation, I'm saying. It's not as complex as the human brain. It's very simple. So till the 1990s, this was discussed, and a lot of people were trying this because the computational power was not much high. They couldn't try very deep networks. So now you can go to the next slide. And I'll just tell you what happened in 2006 when actually all of this changed with one very landmark paper. So I'll introduce a very interesting field in machine learning now. So a lot of theory for time being. Let us talk about some interesting applications. So this is computer vision. So computer vision is something that I worked on for the last 6-7 years. So computer vision is nothing but making predictions or doing classification on anything which is visual in nature. For example, images, video, images mixed with sound, and so on, right? So you can see that there are some images where you can see there is I can't see the screen. Am I audible?
Yes, yes.
Is the screen up?
Yes, you are audible.
Okay, but I can't see the slide for some reason.
Okay, someone is presenting, is showing presenting. Okay, you can pin it up.
Yes. Yeah. Thank you. Yeah. So this is computer vision. So computer vision has to do everything with images, videos, or anything visual. So you have seen a lot of these applications nowadays without actually knowing what is being done in the backend. So I'll be talking mostly about the backend, but you can see that there are, let's say, CCTV cameras, people using drones, people clicking pictures of celebrities. There is Mars rover that you can see in this particular image. So this Mars rover actually is a fully autonomous vehicle that can drive itself in different kinds of terrain. Again, a computer vision application. And you can see the Google Glass, you can see several. So these are several things. I'll also talk about autonomous driving and all those things. So all of these things have to do with computer vision, and computer vision is nothing but using a machine learning algorithm which involves images, videos, and so on. Okay, next slide. So let's try to understand that if I want to give input an image of a cat, okay, if I try to give an image of a cat, then how can I do that? So this image is nothing but a set of pixels. So pixels are nothing but numbers, and when you give these numbers, what you have is these are something that can be even given as an input to the neural network, because neural network obviously, or any computer algorithm, will take numbers. So you can just convert this image into a set of numbers, and that is nothing but a huge matrix. You can convert that matrix into an array or a vector, and then give it to an input as in a neural network. Okay, and you can see that there's a function on the right hand side which says classify image. There's some magic happening over there. We'll talk about that, and then it returns the class label, or returns to which class it belongs. It's a cat or a dog, or what kind of an object it is. Next. And we'll be talking about some problems if you try to do this. So if you take the image of a cat from various angles, okay, so these numbers will obviously change, right? So it doesn't remain the same number. So there is no way that a neural network will actually be able to memorize something. So it is not actually memorizing, it is trying to learn. So there is a very subtle difference between learning and memorizing. So when you memorize, you have to have that exact thing in an exam paper to come, and then only you can write. If there is a slight change, then you will be wrong, right? So memorization is not an option here. So we'll have to see how models can train and can give very accurate results, even if you click the image of the cat from different angles, okay, which results in different pixels. Next slide. So then there is a lot of background information. For example, if you're clicking an image of a cat, there is a lot of things in the background. So you have to teach your model not to focus on the background, but to focus on the foreground. Okay. So then there's something called object detection, which you can do, which will basically separate the background from the foreground and only give you the foreground, because you don't want your neural network or your model to see any of that background, because that background is totally irrelevant as far as the classification task is concerned. Next slide. So then there is change in illumination. So for example, you can click your picture or picture of your cat in different illumination, bright light, dim light, nighttime, complete darkness with a lot of backlight on the right hand side. And even when you have these different illumination, you will have again the pixels changing. Okay. So, but if you build a proper neural network and if you build a very good model, that model will actually be able to ignore the effect of illumination and focus on the discriminative properties of an image. So by discriminative properties, I mean, what is it in an image that lets you discriminate between a cat and a dog? So you have to focus only on that, which human beings also do, right? Whenever you see somebody in the dark, you can still recognize the person, because you do not focus on the illumination, you focus on the facial features, which are the discriminative properties. Okay. So again, if you train a model using this, the model slowly actually will try to ignore all of this extra stuff and will focus on the discriminative part. Next slide. So then there's occlusion. So occlusion is nothing but there's an obstruction in the front. Okay, somebody is, maybe some cat is inside the grass, or on the right hand side you can see a funny picture where the cat has hid inside a pillow, but you can see the tail. So this is occlusion. This is again a problem in computer vision. So there has to be objects, there can be objects which are occluded, but even if they're occluded, you will be still be able to give a correct prediction if you have a very good model trained. Next slide. Okay, so there is interclass variation. So interclass variation is nothing but intra-class. So intra means within class. So basically in a particular class, let's say if dog is a class, cat is a class, there would be different kinds of cats, right? So all cats will not look the same. They can be of different color, they can be of different facial features, they can be of different sizes and so on. But a proper neural network model or a proper machine learning model will be able to incorporate all these differences and still give you a very accurate result as to is this a cat or a dog. But there's a but, you have to train that network with enough number of images and enough these kind of variations so that the neural network understands that even if these variations take place, that is still a cat. Okay, next slide. So this is again an example of image classification. As we talked about, just to recap, we have different training data with labels, let's say deer, bird, plane, cat, and car. And then you have the query data on the right hand side. So query data is nothing but the testing data. After you train with the training data, you give the query data. And there's a concept of distance metric here. So distance metric is nothing but, instead of a neural network, if you try to construct some kind of a distance or some kind of a number as to how similar this query data is with the training labels, you can still get a number which will give you how similar is this query data, for example, with a deer or a bird or a plane. And when you get these similarity numbers, you'll see the similarity numbers would be very similar to a cat. Okay, so this is actually what the neural network does while it trains. Next slide. So this is again this particular problem in the setting of a neural network. So you have an image on the left hand side. You have a lot of different numbers because 32 plus 32 plus 3. So 32 plus 32 is the resolution of the image, width and height. Cross 3 is because it's an RGB image, which is like red, green, and blue. There are three different channels, as some of you might know. So there are 3072 numbers in total, which goes into the neural network. So this F function is basically the neural network. So neural network is nothing but a function actually. So it's a function which transforms the input into the output class level. And during this transformation, that decision, that crucial decision thing is taking place. Okay. So W is nothing but the weights of the network. So all of those weights, if I group them into a single quantity and call it W. Okay. So this W basically determines what is the decision taken by a neural network given an input. Okay, and this W can be very large. It can be, let's say, as large as 100 million numbers or 100 million weights or so on. Okay, depends on what is the size of a neural network. And you can have 10 numbers. So 10 numbers on the right hand side, because let's say if you have 10 classes. So if you have 10 classes, you have 10 numbers, and then each of those numbers will determine whether that particular image belongs to that class or not. Next slide. So this is a little more technical definition. So you have the image on the left hand side. Let's say it's a 2x2 image. You have the W. You multiply the image with the W. You add the bias. Bias is nothing but an extra parameter, and you get 3 different scores here. For example, let's say there are 3 different classes. So when you have the dog score at the highest score, so 437 for 9, you conclude that the input is a dog. Okay. So whatever the highest score is on the output, you will make the decision that the input belongs to that particular class. Okay, this is a very simplistic view, but this is something that is done by a neural network. Next slide. So again, you can see there can be a multi-layer neural network which has activated neurons, and then this is what is making you helping you with the classification task, or whether it's a dog or a cat. Okay, and these connections that are there in the activated neurons that you can see, these connections or these weights are the most important thing, or if I may say, they are the most important thing, which will actually decide as to your input belongs to that class or not. Next slide. So in 2006, this world of neural networks changed when Jeffrey Hinton and Ruslan Salakhundinov, so these are 2 scientists, they were working at the University of Toronto at that time, and Jeffrey Hinton was the same person who invented backpropagation way back in 1986. And he was working for the entire time on neural networks and how to make and how to train efficiently more and more deep networks. Okay, and he came up with this idea of reducing the dimensionality of data with neural networks. So this paper is published in Science journal. So Science is, some of you might know, is one of the world's most celebrated and high impact journals, and they only publish journals. They don't publish articles in computer science. They only publish articles which have a direct scientific and mathematical impact. So this was actually a scientific paper which actually taught that neural networks can actually learn from the data, and neural networks can be trained in a deep fashion. So they introduce a technique known as stack training. So I will not go into detail of that. So that actually copes up with the vanishing gradient problem. And then after 2006, people were able to train very, very deep networks. And the more deep they went, the more complicated tasks they could achieve using a neural network. Next slide. So now is the transition from deep learning from machine learning. So in machine learning, you have the input, you do some feature extraction. For example, we told about those things, right? If you want to accept a job, you will see what is the salary, you will see what is the job perks, you will see how's the job atmosphere and so on. So those are features, those are attributes. Then you put those attributes in a classification model in a neural network, and then you get the decision.
Dr. Ghosh, you are not audible.
It's not audible, sir.
Dr. Ghosh, you are not audible. Please wait. Dr. Ghosh is disconnected. He will join very soon. Due to network problem, Dr. Ghosh has disconnected. Please wait. He will join very soon.
Yeah, sorry for the interruptions. I'll just. Am I audible?
Yes.
Yeah. I can't see the slides now, I think. Yeah. Okay. Thanks. So now in a deep learning model, what happens is we don't need to do any sort of feature extraction. We directly give the input into the model, and the model itself understands as to what part of the input it should look into to get that output, and it wants, a perfect output. So we don't need to do any feature extraction in deep learning. It's completely end-to-end process where you give the input to the model. You have obviously some more number of layers, because the initial layers, what they do is basically they filter out the important part of the input from the rest and reject the others. And then the subsequent layers, what they do, they actually transform that input into the classification decision. Next slide. So I'll go a little quick because I think I've taken a lot of time. So now this is the three things that we have talked about: AI, machine learning, and deep learning. So AI is anything that can sense, reason, act, and adapt. Okay. So things that people were doing in the 1950s, trying to emulate a person playing a game or trying to defeat a person using a computer program. So all of that was AI. Now inside AI, this thing came up known as machine learning in 1970s, where people tried to emulate a person by making a program which learns from experience and data. So that is machine learning. And then inside machine learning, there is deep learning, which is extremely specialized machine learning algorithms, which is based on multi-layered and very, very deep neural networks, which can learn from vast amounts of data. So that word deep actually came into being because you can train a very deep network. Okay, so it's a jargon. People do not, some people would not agree with this word. Some people like to call it representation learning, but this is what it is. Okay, next slide. Okay, so this is a very landmark paper in 2015. So this is in Nature. So Nature, as you know, is the world's most impactful journal. It's a 150 years old publication, old journal. And in 2015, these three authors were invited to write a paper in Nature on deep learning. So Nature, very, very seldom, they do not generally invite people to write papers. So very celebrities, like people who have got Nobel Prizes, those kind of people have written invited papers in Nature. So Jan LeCun, Yoshua Bengio, and Geoffrey Hinton. I'll talk about these three guys at the end. So Geoffrey Hinton, you can remember the guy who came up with backpropagation in 1986, again came up with that science paper in 2006. So these three guys are known as the fathers of deep learning, and they were invited to write this article in Nature, and they talked about what is deep learning and what is not. And you can just go to this article and read it. It's a very, very nice article written, and beginners can also understand. So Jan LeCun is the person who came up with convolutional neural networks, which are the fundamental core of any image processing or any computer vision classifier that you deal with nowadays. Yoshua Bengio came up with GANs. I'll talk about GANs, and then Geoffrey Hinton, you know. So this article again is a very famous one. So let's go to the next slide. And this is some news that come up with deep learning each and every day. You can see these are some snapshots. People are saying that, okay, deep learning will create an age of robots, and then is Google cornering the market on deep learning and so on. So deep learning is everywhere in the news, and deep learning is so impactful nowadays that it has become frontline headlines of a lot of news channels and news publications around the world. Next slide. So let's talk about this very exciting thing known as generative adversarial networks. I'll just try to wrap up quickly. So this is nothing but a specialized set of neural networks, and what they do is that they try to generate synthetic data. Okay, so so this was introduced in 2014 by Jan Goodfellow's group in U Montreal. So this is what it does basically is it tries to generate samples of data which are synthetically generated. Okay, so all of this time till 2014, people were only focused on making predictions. So now people are focused on, okay, can we generate something which humans can do? So humans make decisions. That's okay. That was solved. That was solved using deep learning. Now humans can also generate, humans can also generate new things. For example, I generate a new painting. I sing a song. I write a new lyrics. So can I teach computers to do this thing as well? So this will actually, what will happen is we can generate an exact emulation of a person who can generate new things. Okay, and this is nothing what, and this is what generative adversarial network does. So there is a network. So there are two things here you can see in this diagram, G and D. So G is the generator, which is nothing but neural network. D is the discriminator. It's also a neural network. So what it does basically is, I'll not go into much technical details. A generator tries to generate a fake sample from noise. So this is very interesting. You're generating a sample from a noise, and that sample you are generating can be an image, can be music, can be art, can be sentences, can be a novel as well. Okay. So now this goes into the discriminator. So the discriminator, what it does is it basically says that, okay, whether this generated sample, does it look real or does it look fake? If it looks real, the generator gives an output that, okay, this is good, this looks real. If it looks fake, it gives an output, it is fake. So the discriminator has a loss. So we were talking about that loss, remember, when we were talking about neural networks. So the loss of the discriminator, if I back propagate the loss of the discriminator into the generator, what happens then? What happens is the discriminator now gives a feedback to the generator that, look, you are generating something that's all right, but I don't think it's very real. I don't like it. Try to generate something better next time. Okay. So this is exactly how a teacher and a student operates. A student writes something in the exam, the teacher gives him marks and says that, okay, this is not good. Next time, please come up with a better answer. So what happens is, if you do this thing iteratively, we have been doing this thing iteratively from birth, right? We are writing exams from the past so many years. And every time we write an exam or every time we write a test or a class test, what we get is marks. And that marks tells us that, okay, you are not good this time, please do better next time. So what happens in this process is we learn to create. We learn to create good answers for questions. We learn to create, let's say, pictures or images or whatever, or a novel, maybe, let's say. So using these things, now people try to generate synthetic data, and we'll see what kind of and to what extent they have gone on this. Next slide. So in 2016, there was a paper which actually talked about generating synthetic images, and there were a lot of papers after 2014, after that initial paper came up from Jan Goodfellow's group on GANs. So in 2016, people generated a set of images and published a paper in NIPS. So NIPS is Neural Information Processing Systems. It's one of the best deep learning conferences it held worldwide. It's held annually every year. Last year it was in Toronto. So in this particular paper, they generated some fake celebrities. So if I tell you that, so these images look really nice, right? They look really nice, high resolution, perfect, awesome. But what if I tell you that these people actually do not exist? These people actually do not exist. So these are synthetic celebrities that has been generated by a GAN. So now you can understand what is the power of GANs. So you can generate synthetic images and people have no idea about whether that image is actually a synthetically generated image or a real image. Okay, so this particular paper changed the world a lot, and there was like a New York Times front page article on this particular paper, and people were talking about, oh my god, now you can generate synthetic stuff, and then what not will happen. So this is extremely exciting that you can generate synthetic images and they look so real that you won't be able to make out whether these people actually exist or not. Okay, next slide. So now not only generating images, you can generate images from text. Okay, so let's say if I give you a description, for example, a bird is red and brown in color, stubby streak, something of the description. So using that description, I can teach a child to draw an image. I can also train a neural network to do the same thing. So you will be amazed to hear that the neural network which was trained on these particular or trained on this task, basically creating images from text, did not see these kind of images at all in the input. It does not know what a bird who is yellow looks like or what a bird with large beaks looks like and all. It completely generated from text because the neural network actually understands, now has tried to understand or has actually understood the meaning of text, the actual meaning of text. So this is exactly what a human being can do. And now you can see that human being, obviously you can, let's say, create a picture from a description, right? But what if I tell you that create a picture from a description, let's say 100,000 times in a day? You can't do that, right? You have only some fixed capability. But once you have a computer program to that, you can have thousands and millions and billions of images created from any description. So next time when you go to Google and search for an image, you will actually be seeing that you will get several. For example, you go to Google and search, let's say Barack Obama, okay? And you go to Google, let's say you search with, let's say, a robot who is walking, something of that sort. So when you search a robot who is walking, before 2016, Google used to match that string with the strings that are available in different web pages and give you images. But after 2016, what Google does is it actually has a generative adversarial network inside, which transforms that image into description, which transforms that description into images and then matches that images with other images online. So you get lot and lots of good search results, right? So this is the power of GANs. Next slide. So now you can generate aging. So for example, you want to see how you look when you be old. So you have seen several Facebook apps which says that, okay, if I am old, if I'm 80 years old, this is how I will look. How do those apps work? So all those apps will work on generative adversarial networks. So they were not available before 2014. In the last 3-4 years, these apps have come up, and every app that you see generates a new image of you. How would you look if you're a celebrity? How would you look if you're old? How would you look if you're a female? How would your baby look? All of these things comes from GANs or generative adversarial networks. Okay, next slide. So this was a news in the Guardian newspaper, which is one of the most famous newspapers in the world, and it says that you thought fake news was bad. Deep fakes are where truth goes to die. So deep fake is, and again, a very advanced version of generative adversarial networks that have come up in the last 2 years. So deep fake is nothing but the power of deep learning with the power of generative adversarial networks. And using deep fakes, you can generate videos of people saying something which they have never said. Okay, so you can make a video of Barack Obama saying that I will rule the world or I will go to war with this particular country, but Barack Obama has never said that. But you can generate an absolute real looking video of doing exactly the same thing using a deep learning algorithm. Next slide. Okay, so when you go to Amazon or Flipkart or Jabong or whatever and you shop for different clothes, you might see some people posing with those pictures, right? And posing with those different clothes on. So you want to try a jeans or let's say a top. So you will see a person who is posing with that from different poses, right? So you will be amazed to hear that all of those poses are not actually photographed. So if you have to photograph a model for let's say 20, 50 or 100 different poses, that model will charge you some amount of money per pose, right? But if you take one picture of that model and if you can generate synthetically real looking, absolutely stunning images of that model using that same cloth in different poses, that is what is being done using GANs. So this is a paper which came out in 2017, which showed that that exact thing can be done. Next slide. And you can do from sketch to images. So you can have some sketches of let's say some bags or some shoes, and you can transform them into images. So again, images is what you are generating. So when I was talking about GANs, remember I talked about from noise it is generating. So GANs not only can transform noise to image, it can also transform from image to image. So if you have an image and if you want to transform that image, you can also do that. For example, you have an image of you and then you want to transform it into another image. Well, let's say, how will you look when you're old? You can do that. And this is an example which you can see, and you can see these colors being generated by the GANs. These colors are not present in the input at all. So these are all novel colors being generated. And you see the middle row where there's a bag which has some kind of a leathery color, which it has learned from that input data that bags generally are brown in color. Okay, something of that sort. Next slide. Autonomous driving. Okay, this is another application. So we move out of GANs now and we move on to some general applications of deep learning. Autonomous driving is a very, very vibrant application of deep learning. So when I went to CVPR in 2019, last year in Los Angeles, so I was talking with a lot of folks over there. So they were like people from MIT and Harvard over there, and they were building some autonomous cars, and now they have started building autonomous trucks. So autonomous driving is nothing but self-driving vehicles which has no driver. It will be a completely driverless vehicle, and it can drive you to mountains, through roads, and so on. So MIT recently has developed an autonomous truck actually, which can actually drive in extreme weather conditions, in extreme terrain as well. So all of these autonomous driving applications come up when you are trying to develop self-driving cars. For example, Tesla, I think last year they came up with a self-driving car. You have Mars rovers also. That's also an autonomous vehicle, completely in autonomous environment. No human beings are there. So it drives on its own using the terrain and sees that. So this is again based on an reinforcement learning algorithm, which I did not talk about, I think. So reinforcement learning is nothing but learning from experience. So when a child falls down, he sees that if I walk in this way, I'll fall down. So by the way, walking is actually a very, very complicated process if you don't know that already. So I was talking to some people in Harvard last year. So they were saying that they were trying to build a robot that walks, and it took them at least 6 years from 2005, 2010 or 2011 to make actually a robot which works, because walking is a very complicated operation and you have to do very subtle balancing of your body in order to walk. So and you'll be amazed that you do that every day without even thinking. So it has become so much embedded in your nervous system that you don't have to even think when you walk. You can balance that on your own because that's an autonomous part of your nervous system. Okay, next slide. Again, speech recognition you use every day. You use Google Now, you use Siri. So whenever you are saying something to your mobile, you say that, okay, set an alarm at 8 p.m. or what is the nearest Italian restaurant or something of that sort. So then you get an answer, you get a web search, and you get all sorts of stuff. So everything that you see on that particular application is a deep learning application. And speech recognition is a very, very major application of deep learning. Next slide. Okay, so we generate music. So using deep learning algorithms, people have generated music. And they have generated raw audio, and they have not only generated music, they have generated people speaking in different languages. So for example, if you speak in English, that can be translated to, let's say, Chinese. You can do that in text. That was there before 2010. But now people have started emulating your voice in a different language. So for example, let's say if you speak Mandarin, if you speak French, or if you speak German, how would you sound? And what kind of things you can speak? So that can also be generated, okay? And completely based on some kind of GANs and some mixture of GANs with CNNs. Next slide. Okay, the last application. So deep learning in medicine. So this is extremely exciting. So this is a New York Times article on the right hand side that you can see. It says that making new drugs with a dose in artificial intelligence. So what they have done is, so there's a competition that is held worldwide. So that competition is called the protein folding problem. Okay, so that is, so I don't have a very good understanding of that, but it's something that which predicts that what kind of molecules will bind to a protein, and that is a very integral process in developing of a new drug. For example, now you see people are trying to develop a drug for corona, let's say, okay, for the coronavirus. So you have to understand to what proteins does coronavirus bind onto, and then you have to target those proteins if you have to build a drug. So very naive explanation of what is being done, but it's a complex process. So in this competition, there were several deep learning researchers that actually took part. And people were making fun of them, and they were saying that, oh my God, you guys don't know chemistry, biology. How would you even think about competing in this competition? And this competition, you'll be amazed to see, was not won by academics. It was won by DeepMind. So DeepMind is a company that is being owned by Google now. So that company actually develops deep learning algorithms that emulates the human mind. And a bunch of people working at DeepMind, they are some of them were scientists, some of them were engineers. They actually came up with the winning formula, and they won this competition. And those people, they did not have any background in chemistry, biology, or life sciences, and all of this thing they did in just 2 weeks. So you can understand the power of deep learning. You can develop a new drug using an algorithm and developed by people who does not have any idea or any knowledge in chemistry, biology, or life sciences. And they have actually won this competition. And after this thing came up, and after this article in New York Times front page in 2019, so the entire pharmaceutical world was like, oh my God, what is going to happen now? So if deep learning takes over pharmaceuticals and about drug delivery and drug discovery, then you can imagine that the entire pharmaceutical industry will, they'll probably collapse or they'll be in panic. So they are already in panic due to this particular algorithm. Next slide. So my second last slide. So these are the three pioneers of deep learning. On the left hand side, you see Jan LeCun, who is the father of computer vision and develops CNNs, and any algorithm that works on images and videos are actually working with a convolutional neural network, which has been developed by Jan LeCun. The middle guy is the great grandfather of deep learning. He's Geoffrey Hinton. He developed the backpropagation algorithm in 1986, and then again he came up with that science paper in 2006. So he's the one who actually has worked his entire life on neural networks, and you will be very excited to hear that his background is not in computer science. He is a PhD in psychology. So he used to teach psychology, and from there he tried to understand how human neurons work and came up with this entire mathematical model of neural networks. The guy on the right hand side is Yoshua Bengio. He's the father, he's the inventor of generative adversarial networks, or GANs, that I showed you, generating synthetic data. And these three guys won the Turing Award in 2018. So Turing Award, as you know, is often well known as the Nobel Prize in computer science. It's the highest award in computer science. And the award is given by ACM every year in their annual event in San Francisco. So these three guys won that award. So Jan LeCun currently is the director of AI at Facebook. Geoffrey Hinton still teaches at University of Toronto, is also distinguished researcher in Google. The right hand side, Yoshua Bengio, he is still a professor in University of Montreal in Canada. Next slide. So my last slide is on the research impact of deep learning. So some of you might know that whenever you have to understand whether a conference or a journal publication that you publish in a conference or a journal is good or not, you should go to Google, and there's something called Google Scholar Metrics. So there's something called H5 index and H5 median. So this is nothing but a number that gives you how good or how impactful that publication is. So this is the list of the top 15 top publications in the entire world. And that includes everything from science, art, astronomy, physics, chemistry, engineering, computer science, everything, right? And you can see on number 5, there is this IEEE CVF conference on computer vision and pattern recognition. That's CVPR that I was telling you. So CVPR is right now at number 5, and you can see in the top 15, there's not a single publication from computer science, not a single publication from engineering itself. So all of those are science publications, and CVPR is the only one that makes it to the top 5, and it's right now the top 5 most impactful publications in the world among all areas of engineering, science, arts, and everything. So I was very fortunate to get my paper selected in CVPR last year in 2019. Took place in Los Angeles. So I went there, and it was an amazing event, and you won't believe what kind of stuff takes place over there. And every company you can think of, like Google, Facebook, Amazon, Adobe, Nvidia, you can even Tesla, anything you can think of will come to that event, and they will have their people presenting papers, and there are a lot of exciting stuff going on. So I want to encourage all of you guys towards deep learning, understanding deep learning and machine learning, and try to take up higher studies and invest time on this particular area, because this is going to change human lifestyle forever. And it has already changed a lot, but it's going to do some crazy stuff in the next future. There are a lot of other applications I did not show. For example, there's something called computational art, where you can generate paintings, you can generate novel music, and so on, and crazy stuff is being done. So all of you guys would be very excited to hear this, and I would encourage you to study this particular thing. There is no prerequisites required to study this. As long as you know multiplication and addition, you can study deep learning, because a neural network is nothing but multiplication of weights and addition of those weights and taking a summation. That's it. Okay, a little bit of derivatives. That's all. So thank you so much for this opportunity to speak, and I'm sorry for the interruptions that were there, but I'll be happy to take questions from you, and please feel free to ask anything you want. Thank you.
Thank you, Dr. Ghosh. Am I audible?
Yeah.
Thank you, Dr. Ghosh, for your wonderful lecture. It was very exciting, and it was a thorough journey from the artificial intelligence to deep learning via machine learning, and you highlighted different aspects and real life applications, and also highlighted the future of our mankind in these fields. So now I would like to start the discussion. We already have few questions.
Yeah.
From Shuday, he asked which method is best for machine learning classification.
Okay, so machine learning classifications initially was done using neural networks. Then came there are other algorithms called support vector machines, and it keeps on changing. There's not a single algorithm that is best at everything. So if you talk about, let's say, generating synthetic data, you have GANs. If you talk about classification, you have neural networks. If you talk about classification in computer vision, then there is convolutional neural networks developed by Jan LeCun's group. So there are different algorithms, and I would say that no single algorithm works best in all scenarios, because you would know that since these algorithms are emulating a human being and emulating a person, no single person is good at everything. Some person may be good at music, somebody may be good at science, somebody may be good at sports, and so on. So depending on the data and depending on the scenario, you can try different algorithms and you will get different results, and then that is how you should be investigating these things.
Thank you. Second question from Promila is, how does the weight determine the value of the output? Again, which language is best to work with arrays of an image?
Okay, so what was the first part of the question?
How does the weight determine the value of the output?
Okay. Yeah. So what the weights, what we do using those weights is basically we multiply those weights by the input, right? And you get a next set of numbers. So you do a summation of all those numbers, and then you go to the next layer and you repeat that process. So if you repeat that process, you will be doing a feed forward operation through that neural network, and when you arrive at the output finally, you will have a number in the output, right? Now when you have that number in the output, what you will be doing is you want to construct a loss function using that number, right? And that loss function's derivative with respect to the weights will basically tell you as to how you should change your weights so that you get a lower loss next time. And that is one thing. And if you talk about languages, so there are a lot of platforms which are currently being used by people. So I will just mention some of the top ones. So there is Python, which is being used as a basic backend language for all machine learning applications right now. But Python is not the only language. So people, when I went to CVPR, I met some people from autonomous driving industry. So they were talking about they use C++ because they have to interface a lot with hardware. Right? But if I talk about classification and general applications in machine learning, Python, I would say, is the best language, because on top of Python, you have several libraries that will help you create neural networks. For example, there is I will mention two of them. So one is PyTorch. So PyTorch is a set of libraries that were developed by Facebook around 5-6 years back. And then there is TensorFlow. So TensorFlow is another set of libraries which also works on top of Python, and that is being developed by Google. So Google and Facebook, they often fight with each other on these platforms, but you can choose any one of these two, PyTorch or TensorFlow. But both of these set of libraries will actually work on top of Python.
Okay. Thank you. Next question is, want to classify CCTV image using Python? Which interface can be used to do the project?
Okay, so yeah, so you can, so if you want to classify images, so Python itself has a set of libraries known as sklearn. So sklearn is basically a set of libraries which will allow you to create some simple classifiers like decision trees, neural networks, support vector machines, and so on. But if you want a very advanced level of an architecture, so by advanced level I mean if you want to customize your neural network to a great extent, so I would then suggest go to either PyTorch or TensorFlow. But PyTorch would probably be a little easier one. TensorFlow is a little different thing, but TensorFlow is slightly more powerful than PyTorch. But you can use either PyTorch or TensorFlow. And Python, if you want to create a very simple application, I think Python itself does have sklearn libraries which can do that.
Okay, thank you. Next question is, how ML or AI is used in analyzing remote sensing data?
Oh, okay, yeah. So remote sensing, yes, yeah. So when we are trying to analyze remote, when we are trying to see remote sensing data, so there are a lot of companies who are working on, discovering minerals using remote sensing, discovering, roads, or trying to understand the road network of a particular country. So I will just go ahead a little bit from remote sensing, and I'll say that any kind of satellite image can actually be used as a in a classification scenario, and you can actually build a classifier to teach the classifier in order to understand whether a part of a satellite image is a road, or is it a building, or is it farmland, or is it a forest, or is it a river, or so on, right? So using this simple technique, if you have a supervised data, so if you have data where you have initially labeled some samples from remote sensing images and say that, okay, these remote sensing images correspond to these different things, and if you then try to train a network, what will happen is you'll have a network which will then be able to classify different parts of a remote sensing image into different categories. For example, let's say this can be a place where there is some mineral available, this can be a place where there can be a forest or some kind of weather condition and so on.
Okay, thank you. Next question is from Orikhan Chatterjee. Can this technology be used to create linguistic text by following natural language that reads as unsuspecting and fluid as the images? Fascinating facts.
Yes, absolutely, yes, and it has been done. So after generative adversarial networks were there in 2014, people have actually tried to generate stories, stories, text, even novels. So people have come up with stories which actually feel like a human person has written it. But see, so this particular area of machine learning is known as natural language processing, NLP. So NLP entirely deals with text. Okay, it's very different from computer vision, but in NLP, it is really difficult to it's easy to come up with maybe a couple of sentences or 5 sentences, right, that can sound very real. But when you come up with a novel, or when you come up with, let's say, 15, 20, 30 pages of text, what researchers are trying to understand is how can you generate that text so that there is a connection in between. So when you read a story, there's a connection between every paragraph, and there's a particular flow of that storytelling. So storytelling itself is a research area in NLP. People have been able to create some short stories of 5-6 pages, but I am not sure if they have come up with something as crazy as like coming up with a novel of 500, 200, 500, 600 pages. That would need some more time in research. But yes, people have come up with algorithms for creating language. Yes.
Okay. And he also asked, can you kindly suggest some basic books to learn deep learning?
Okay. So when you want to learn deep learning, I would strictly suggest you not to go for books, because till 2015 there was no book in deep learning. The first book in deep learning came out in 2015, which was by Jan Goodfellow. So that the name of the book is Deep Learning by Jan Goodfellow, the guy who came up with GANs. So if you read that book, I don't think you would understand a lot of it, because it's very mathematical. So I would suggest you to start from some very wonderful video lectures that are available freely on YouTube. So Andrew Ng, he's a professor at Stanford. He has a lecture on machine learning, and that lecture is quite old. I mean, it's like a 2014 or 2015 lecture, but he's the one who actually came up with this idea of teaching machine learning to people throughout the web, and he's also the founder of Coursera, if you know Coursera, what Coursera is. So you can start from that, and then there is another lecture known as convolutional neural networks for computer vision. The name of the course is CS231N. So it's a Stanford University course, and it's Karpathy and his folks created that course, Professor Fefeli's course. So you can, the lectures are available again on YouTube, CS231N, and you can see that it does assume that you know something about neural networks, does not assume a lot, but if you know how basic machine learning and neural networks work, you can still see that course, and that course will take you from basic neural networks to the most advanced algorithms in deep learning.
Okay. And our last question is from Kamala Gupta. How to differentiate between real image and these created synthetic images? How to regulate misuse of such technology?
Okay, this is a very good question. So after these kind of things came up, people are actually now trying to again generate a set of machine learning algorithms which can actually tell you whether this particular image is real or fake. Okay, but the problem here is that you are using that same algorithm to generate a fake image, and then you use a very similar kind of a model or network to detect whether it's real or fake, right? So if you have generated that image very nicely or in a way which can actually fool your neural network or fool your classifier, it will be a very hard time for you to actually come up with an algorithm to detect whether it's real or fake. Okay, so the problem here is the person who is generating the fake image is the same person who has been told how to detect it. So if that person is very interested in generating the fake image, he might not be able to detect his own fake images from real ones because he generated some really awesome fake images in the first place. So it's a difficult problem. People are working on it, and there are some algorithms now. So I was working in this image analysis biometrics labs in IIII Delhi. So they also were working on an algorithm, and we had some papers published, and where we tried to build a classifier so that to tell you it's real or fake. But I won't say that that technology is still 100% successful. People are trying it. Maybe in future people will do something like that.
So thank you, Dr. Ghosh. I think this is the end of our discussion session, and we have come to the end of this webinar. Now I would like to request our Honorable Principal Sir, Dr. Shantanu Chakraborty, to say a few words and end this webinar. Sir, are you there? Sir?
শুরু করব?
হ্যাঁ স্যার।
Okay. Hello. Thank you, dear participants and organizing teachers of Department of Computer Science of Government General Degree College, Singur. I would like to congratulate you, all of you, for a successful arrangement of this webinar. We could learn a lot from this one on the most important data science and deep learning, which are two most dynamic and highly used tools employed from dawn to dusk in and around us. I would like to thank Mr. Orpit Jadhav and Soumyadeep Ghosh for their deliberations. We are enlightened and sincerely thankful, sir, to both of you. The endeavor of the Computer Science Department, their HOD Shandipan and Shomit and Anupam, is really praiseworthy. IQAC of our college is continuously supporting many such events regularly organized by our college. Last but not the least, the support of all the faculties of this college who are constantly supporting all the events crossing the barrier of the subjects is gratefully acknowledged. I thank all the participants once again for making this program a success. Thank you all.
Thank you, sir. So this is the end of our webinar, and we are going to organize another webinar in the next Sunday on the topic machine learning, and we will send the flyer soon to you. Hope we will see all of you there. Thank you.
The link for the feedback form is given into the chat box. All of you are requested to fill up the feedback form within 1 hour, and after that will be inactive, and you properly fill up the feedback form, and based on this feedback form data you will get the certificate within 3 days. Again, I am requesting you, all of you, to fill up the certificate feedback form within 1 hour, and it will be active for 1 hour. After that you cannot fill up the form, and after properly fill up the feedback form based on the data you have put it in the feedback form, and the certificate will be generated, and it will be sent within the 3 days to your registered mail ID. Please check the chat box. The link is given for the feedback form. Thank you all. That's we are close of the program for today's program, and we will hope we will again join in the next Sunday for the machine learning webinar. Thank you very much.